to explaining my design process and why I think it's better. So firstly, Newton's third law, equal and opposite force. So we're applying a force into the wind, but that force is also being applied onto our blades. Using momentum theory, we can calculate with that Betz limit there. You've heard of Betz limit 59%. We know exactly how much force we need to apply onto the wind to get that optimum or optimistic 59%. So that's the first issue here. There's a certain amount of force that we must apply onto the wind, and we don't want to deviate from that. And there's also other forces involved there. So how do we do that? We have a wing. Okay, so we have aerodynamic theory here. We can calculate lift forces there. There's the wing shape. We have a high and low pressure side. We have an angle of attack here, and also we have Reynolds numbers for different regimes. So depending on the size and how quickly your blade is flowing through the air, it'll operate in a different Reynolds number regime. And so there is kind of your optimization process conventionally for a wind turbine. You want to, if I go back one step, your lift force here is good. If you think on an airplane, you want lift, you don't want drag. Okay, so the ratio of your lift to drag components, you want as high as possible, as much lift for as little drag, and that's what you're aiming at. So the same thing applies for wind turbines. If you look at your airfoil, the characteristics for an airfoil, for different Reynolds numbers, we will get this lift to drag ratio is represented on the y-axis, and here's your angle of attack. So as you change your angle of attack, so your lift to drag ratio changes, and there's an optimum angle of attack. So if we're on, say, this top curve here, the optimum angle of attack would be 5 degrees. So if you're designing an airplane here, you want your airplane wing to have an angle of attack of 5 degrees to be optimum. Same thing applies to wind turbines, and it makes sense. Lift is good, drag is bad. And then we apply this theory to different components of the blade, but yeah, that's not too important. Okay, so that's the introduction. So focus on, you usually optimize for lift to drag ratio, and there's a certain amount of force that we can apply onto the wind. So now my theory looks at, let's ignore that theory slightly and say let's rather optimize for Reynolds numbers. So how do we change the Reynolds number? There's the equation for Reynolds number. Your velocity that your blade is moving at and your wind velocity, let's say, is a given. Can't do anything there. Your kinematic viscosity is a given. The length or the width of your blade, your chord length, is something that you can change. Okay, so that's pretty much the only parameter we can change while designing a blade. And so that's what I'm playing with. So this is the crux of the way I've gone about it. That would be viewed as an optimized blade design there. And so I've increased the chord length, so made the blade fatter. But in order to have the same amount of force, I have to decrease the angle of attack. You can see that there's an angle to that blade there, and this blade is much flatter. So how is that? Well, let me just explain what would happen there. Okay. So say we're operating on this Reynolds number curve, and we're operating at our max lift to drag point there. I've now said that, okay, we've reached the top of the scale, we can't go any higher. Let's increase our Reynolds number so we jump to the next curve, because there's an advantage in lift to drag ratios there. But I've had to decrease my angle of attack maybe to there. So now I'm operating at that point there. Low angle of attack, maybe a similar lift to drag ratio. Okay, and we see this in this next slide here. You say, what's the advantage of this type of design? And if you look at the two designs that I did for this research, there's very little design in your max power outputs at different wind speeds for the two designs. Okay, so you look there, very, very little difference. So why we do this? If we break it down into your lift to drag optimized turbine, we see the power curves there for the different wind speeds. Okay, so as you change your RPM, your power goes up, up, up until you reach your optimum RPM, and then it decreases again. So that's for 10 meters a second, 9 meters a second, and so on. So what would happen here if we're optimizing for gusty and turbulent wind conditions if I'm operating at 8 meters per second there, now at my max power point there, operating at 500 RPM, and there's a gust up to 10 meters a second. So boom, I'm now not operating on this line, I'm now operating on the 10 meters per second line. So I'll jump up to this curve here, and I'm operating there. Whereas if I increase my RPM, I could have been operating there. But that gust is instantaneous, so you can't increase your RPM. It happens, and so you jump from there to there. Now let's look at the Reynolds number optimized design. Much flatter power curves. So that's the characteristic of this oversizing and increasing the Reynolds number of the blades. What would happen is you would be operating at 8 meters a second there, sudden gust to 10 meters a second, and you're operating there without changing RPM. Very close to your max, your max power point there. And this theory only really applies to low Reynolds number regime. So small wind turbines and very low wind speeds. So this doesn't apply to large wind turbines. And so perhaps the reason why I think this has been overlooked, I haven't come across this in any research or anywhere else. So if anyone's heard of this before, please tell me. So starting to close down now a bit. Potential benefits: increased energy yield, decreased cut-in wind speed. Your turbine performance is less dependent at advanced max power point trackers, so it doesn't have to change its RPM as the wind changes. It's not critical on RPM as much anymore. Increased blade stiffness, because now we have these fatter blades. Possibly less structural material required because we have this increased stiffness. Disadvantages: increased projected areas. We have these fatter blades which interact more with the wind. So we're trying to stop our turbine. There's a lot more surface area. And then, so I've kind of contradicted myself a bit, and I also say a possible disadvantage is you might need more material because it's a fatter blade. And so, in conclusion, well, there's a few more slides after this. The analytical results show great promise for increased energy yield, so especially in gusty and turbulent winds. And then the next step was to confirm this with practical results, which I've already subsequently gone ahead and done. So there is the two designs with, this is a stationary turbine, and all I'm measuring here is the torque against the wind speed. I've locked the blades. So you can see here 8 times the amount of torque generated from my Reynolds number blades compared to your skinnier lift-to-drag optimized design. And then here I've looked at, this is just comparing my power curves. So there's your power coefficients on those axes there, your tip speed ratios. Here you can see the flatter power curve. So that's my analytical result. There's my practical curve. So it kind of fits on. And then this is the lift-to-drag design. So there's my analytical results, and there's my practical results. So also again, correlating quite well, and so I'm happy with that. There's just a few pictures. So here you can see the fat blades that I designed and 3D printed. So we print the blades to test them, and there's the skinnier blades. So you can see the comparison there between the skinnier and the fatter blades. And that's the end.